Okay, Edgar, can you let us know when we're live?
We should be fine.
Okay, I need to check. Okay, so yeah, it seems we're live. So
Fine.
yeah,
Cool.
apologies for the delay, everyone. We're trying to set up Zoom to YouTube, which for some reason didn't want to work. So yes, thanks for attending our tutorial on local features from SIFT to differentiable method. And just a short introduction from us organizers. So my name is Vasilios Holdas, so I'm a research scientist at the FRL. I'm joined by Edgar Riba and Dimitro Miskin, so who will introduce themselves now.
Okay. So yeah, hi everyone. I'm Edgar. So I'm a PhD student at the Computer Vision Center and a research scientist at the Robotics Institute in Barcelona. And I will be covering the part for Kornia in this tutorial. I will give a quick introduction about Kornia, and then I will go through some examples. Dimitro?
Hi, my name is Dimitro. I will present the results of large-scale benchmark on local features and everything related to you mentioned, like matching methods, filtering, RANSAC, so on. And then later, I'll show you a couple live examples of feature matching with Kornia framework, which is our OpenCV in PyTorch, as we call it. So stay tuned and let's start, I guess.
Okay, thanks. Let me start recording so that we can put it in YouTube after. Okay. Let me share my screen. Does everyone see my screen? Okay. Right. Okay, so welcome. This is the tutorial program, just a brief overview. So we start by explaining a bit about classical and modern methods in local features. This will be the first part. The second part, Dimitro will talk about lots of things that are related to the practical side of doing image matching. So he has lots to say about how do you actually do image matching in practice, and if it matters that much, all the previous methods from papers, how did it translate to real world data and in a large scale environment. And then Edgar, I think together with Dimitro at some point later, so Edgar will introduce the Kornia library, which has to do with image differentiability, I think. So one of the main aspects there is to make plug and play differentiable aspects to put in an end-to-end pipeline. So it's basically an OpenCV, as Edgar, I think, or Dimitro said, for the deep learning period. And this is the program. So 9 to 10, we'll do the overview, and then 10 to 11, the from paper to practice talk, and then 11 to 12, the Kornia introduction, and then some hands-on session with Google Colab notebooks. So this is the main website of the tutorial, where you can find both the talks and the PDFs. The presentations will be uploaded after. Dimitri's presentation is already uploaded for if someone wants to take a look together with his talk. So to start, first of all, what is image matching? I'm sure most of you will be familiar with it. So it's a computer vision problem where we try to match individual parts of one image to individual parts of the other image. And this example that you see here, we have a graffiti from somewhere in London, and then any successful method will associate individual points or circles or regions on the left image with where they are on the right image, but also how they deformed in case of the circle, for example, as we see here. So we see because of the change of the camera, the circle becomes an ellipse here. So this is exactly what these methods try to do. And one might ask, why is this thing useful, right? So there's many applications. I will just mention a few of them. So one, probably the most common application is structure for motion, so SFM. That is, you have a set of images and then you try to build a 3D map from these images. So in this example here, which is based on Heatmap, which is an open source 3D SFM actually program. So you can see that the map that was built on top, map of Rome, was built from individual images, I think from Flickr, so from lots of thousands of images. And to do this, you need to do individual point matches between images. So that's why you need image matching. Another useful area is SLAM. So you have something like a video stream and you want to build a map online as you walk down a room. And this is another great area that lots of local and image matching is used. So when you have a map, then you can also use image matching for localization. So you have a new image that comes in, and then you try to match this image with all the previous images in your map that you have already built. And this is one example that from the Escape pipeline that was doing exactly that. So you have an image and then you just manage to match it with your predefined map. Sorry. So this is another demo from Superpoint, Magic Leap's SLAM system that was based on Superpoint. I think it was a quick demo they put on GitHub, but still you can see exactly why is image matching useful, right? Because these individual dots are points that were localized and then they're tracked inside the video, and then that's how you can recover the geometry of the world. So, and then you can imagine that anything that's an application built on top of either SLAM or SFM, it could be considered as an application of image matching. For example, AR applications. So first of all, you have to build the map, then you have to localize to have the capacity, the capability to add virtual objects on top of your map, like it's very commonly used in the AR applications, like the scavenger app you see here. Another application, the last one I will mention, is panoramas. So we've all seen like the panorama apps, or your photo app probably does it now in your phone. So this is probably one of the easiest ways to do panoramas, by stitching together individual images, and by doing image matching, then you can find how one image relates to the other, and then you can blend them in the end to a global panorama. So the question is, why do we need image matching, right? So how is image matching related to all these things? And I'm not going to go into too much detail here because there's no time, but we can basically think it as a way to recover camera positions or movements of cameras. So the idea is you have a scene and you move around, and then by doing image matching, then you can start understanding something about the camera, how it moved, and then by start building observations like this, then in the end you can do triangulation, and then of the points and start building your map. And then when we say triangulation, so this is a very basic example of triangulation, which is you have two images, left view and right view. And then, as you probably know, just by, due to the way the cameras work, you can never be sure about the depth. So each pixel position, you have no information about how far away it was from the camera. So the XL point here, it could be either from X3, X2, X1, or X. So to start getting depth information, understanding how far away things are from cameras, that's why you need other views. And then if you manage to match XL with XR, then you can start building this triangulation, then you can start building your maps. So there are different kinds of algorithms and special cases about how many points you need, but for now, that doesn't matter that much. Let's assume that we're using a standard algorithm, which is the 8-point algorithm. That means that you need 8 matches to recover poses. But practically, we need many more. And this is This is visible here, why we need many more matches, because lots of our matches would be wrong, right? So you cannot assume that you have 8 matches or 10 or 12 and they're all perfect, and then you can perfectly recover the camera motion. So a key aspect of this is RANSAC. So by this, I mean how to remove bad matches. So Dimitri's talk, I think later on, will contain lots of information about this. So I'm not going to go into too much detail. So, but just keep in mind that this is a way to just remove the red stuff from here. So this is an example of SIFT, a well-known 20-year-old, I think, algorithm by now. And then you can see that out of the matches that they found, so a bit more than half are correct. So if we have a way to remove the bad matches, then it's okay, because we can still find a pretty good pose correspondence between the two images. And this is exactly what RANSAC does. And then I don't know how well you can see this image now from YouTube, but you can see that in the third row, you get some bad matches, which are denoted. You can see them by the lines that look a bit different compared to others. And then the fourth row is what is left after you remove the outliers using RANSAC. And then you can see that all of the matches are pretty nicely aligned. So that probably means that the matching is actually correct. Normally you expect lines to have similarities. So when you get lots of lines pointing to different directions, that probably means your matching is not very good. So to sum up, you need to get better ways to match points between two images. Then you can build up better pose estimators or triangulators or SFM methods. And that means you go to better 3D models, which means better panoramas, better AR apps, and everything else related to the applications of image matching. So let's briefly go through the what is called the classical pipeline, although it sounds a bit weird to call it classical, but this is a common term, I think, by now. So everyone means the pre-deep learning, I guess, pipeline by this. So again, to remind what the goal was, we have individual images and we try to recover the camera movement between them by doing matching. So how do we normally do matching in the classical pipeline? Is we detect some points. For example, the green dots you see here, and we detect them on both images. And ideally, these points should be more or less the same, or at least have a very big common set. So after we detect individual points, then we go around each one of them and we try to describe the visual information around this key point or this individual point by something. And this something is something called the descriptor that we'll see later. So if you can imagine this as cropping a small area around the key point and then having some kind of barcode or descriptor, as I said, for each path, which is what you store in your database. So when you want to do matching later on, what you do is you manually compare the descriptors of each path, and then you do some kind of matching, and then you choose the best match for each of the for each path from the left image on the right, and so on. And by that, you start building your matches, which are the lines that you see there, the green and the red line. So this is the standard classical pipeline. So as we said, it has 3 stages: detection, description, and matching. So detection is about choosing the interesting points in the image, because not each point in the image is interesting. Description is how to convert these points or the patches around them into suitable representations. And matching is how do you actually match these representations between the 2 images. So just to show all the possible, not all, some of the possible cases of feature frames or interest points or interesting areas in the image, the question is, how do you represent an interesting point or region in the image? Because as you see here, this can be almost anything you can imagine. So you can have a point, you can have an ellipse, you can have an oriented ellipse, which also has an angle associated with it. You can have a rectangle, you can have a circle. So by you agree on a convention about how you represent interesting areas or points in the image. And then just to motivate this, I'm going to present the most simple example of identifying interesting regions or areas or points in the image, which is the simplest scenario you can imagine. So if you can imagine, you have a sliding window and then you you put it in one position and then you start moving it a bit. And then you measure the differences in intensity, for example, the differences in the signal that you get. So the idea is the green area here, if you see this, so if you move it around, then it probably doesn't change a lot. Let's assume you get the histogram of the paths. So that probably doesn't change a lot, right? Because it's a black area and it's very uniform. So if you go on the other hand here in this area, so if you move a bit, then this changes. So there is the simplest way you can identify interest points. So you can build up the matrix of differences across X and diagonally in terms of the derivatives of the intensities of the image, and then you can get the eigenvalues of this matrix. And then if the idea is if both you can have these cases, both eigenvalues are low, similar and low, close to 0. Both eigenvalues are similar and high, much more than 0. And then one of the two is much greater than the other. So how does this translate in terms of interest points? You can see it here. So if both eigenvalues are 0, then it probably means we're in a uniform area. So this is definitely not an interesting point. So if one of them is much higher than the other, then we're probably along an edge. So it's definitely more interesting than the first case, but not very good, because you can get easily confused when you move along this direction. Then this looks the same as this, as this, as this. So it's probably not an ideal case. On the other hand, in this case, so you see that this is a very repeatable or interesting point, because it's very distinctive compared to the other points around. So this is the simplest way to get interest points. Of course, this is not the only way, and but it's a building block for more methods. So you can also add scale estimation again with many methods. Again, I'll mention probably the easiest one, which is you get an image pyramid, which means you keep downscaling the image by a constant factor, and then you run your original paths on the smaller images, and this increases the area that this estimation is happening to get the interest point. So that's how you can get some kind of scale estimation. So I'm going to mention a bit some relevant methods. One, probably the most well-known method is the SIFT detector and descriptor. So I'm going to talk about the detector in this first part, which is a way to get, again, interest points, to understand interesting points in the image. And how you do this is you build something called difference of Gaussians, or GOG, and by blurring the image and then also changing the size. And then the idea is you go through something called the scale space, and then you find a maxima or minima in this scale space, and this is exactly what is your interest point. So I'm sure most of you have heard about this. You can read more about how it works in the original paper. SERF was a bit later on than SIFT. Again, I'm talking about the detector part here. We'll talk about the descriptors later. So in SERF sped up SIFT just by converting the actual Gaussians that you need to do the difference of Gaussians by something called box filters and integral images, which is something much faster. And it's an approximation, obviously, because it's rectangular, but it's still a quite good approximation of the Gaussian kernels. So this showed similar performance to SIFT, but with much faster execution time. So this is one way. Gaussians are one way to get the signal that you need to identify interest points, and it makes sense because you can convolve your image with these filters, and then you can start finding minima and maxima. So it's not the only way, and there are several other methods that extended this idea. So this is one method that you can see that uses a bank of filters with different orientations, and these things are convolved and in the end combined to get, again, aggregated results, and thus getting the interest point. There are lots of other methods. I'm not going to mention all of them, but just to motivate the discussion about differences, there's a method, the MSER, which focuses on getting a segmentation of the image, and then from this identifying something called stable external regions. So extremal regions, sorry. So, and this has to do basically with trying to segment the image and then associate one ellipse with each of the segments. And this is a quite robust way to identify interesting areas in this case, because they're not key points anymore, they're ellipses. Another thing you could do is to just design a machine learning method that tries from a path to do some individual comparisons based on the intensity, and then given predefined thresholds that are learned online, you can then decide if the whole response is more than the threshold, then I assume this is an interest point. If not, then it's not an interest point. So to sum up in terms of key points or interest points or feature frames, however you prefer to call them. So there are many possibilities for types, and they might include scale and orientation. This is the things that you probably need to remember. And this is one example of running different methods in the same image. And then you can see how each different method can produce different, first of all, sizes or styles. So you see some methods focus on the bottom area, some others don't. So this is very related to each individual method. So the next thing that's very important, if you remember from a classical pipeline we saw, is how do you get from feature frames or interest points to paths? So this is, for example, if you have already detected the regions, which could be done with any of the methods we mentioned before, and which you can see here from the green regions. So the idea is, how do you convert this to an actual vector that you can then compare with other vectors to see if they match or not? Probably the easiest way to do this would be to just use the intensity, but this is not obviously a very good way, because imagine if you change the, if you turn a bit the lights on and off, then it completely changes the values, so it wouldn't work as a descriptor. So that's why we're saying that the descriptors should be at least more discriminative and robust than the original paths otherwise, and also ideally much lower in dimensions. So if you have a 32 by 32 paths, then you have 1000 values, 1024 values, and if your descriptor is 2000 values and it's not much better, then it's probably not a very good descriptor. So, and then this is quite challenging, because if you see on the bottom, this is an example of kind of things you expect on real maps, on real images that you observe, real patches that were extracted around key points that represent the same point in the 3D map, in the actual map, which in this case is the top of the building. So you see things like day, night, reflections, colors change a lot. So this is a very challenging set of changes to represent in one small representation, which is the descriptor. So another thing to consider is that changes in orientation might completely change the final paths, and thus make it even more difficult for the descriptor to be robust. So in this case, I just flipped the image and then extracted the same paths on the same position. So you see that all the gradients now look in the different positions, right? So this is quite challenging for some way to describe this. So again, starting from the very simple examples, SIFT was, it had two parts, as I said, the detector and the descriptor. So in the descriptor part, what the author of the SIFT paper did is that you just split the space into a grid. For example, you can do 4 by 4, and then you can also try to aggregate all the gradient orientation. So you get your image, you get the gradient of your original image, and then you start aggregating orientations into bins. So you can have, for example, eight bins, which means that the total of 360 possible angles, you just bin them into 8 big groups. And then, for example, if you have 16 areas and 8 orientations, then you can start building a descriptor by combining everything, the small local histograms, and then you end up with a histogram in the end that is bigger dimensionality. So in the case of the original SIFT paper, that was 128. This is an example of how it looks like in a real image. So you have the grid, which is 4 by 4, and then you see these individual things you see here represent how much, how big the signal responses in this direction in this specific part of the paths. So this is an image from VLFit, which also has some other very nice visualizations of grids and responses. So it's, if this is something that interests you, you should take a look at the original VLFit website. So again, similarly to the detectors, you can start building different ways of aggregating your local stuff into a bigger descriptor. So you can say, instead of the actual grid, instead of the rectangular grid, I can do it circular grid. So that might help with the rotations, for example. So this is one such case of a descriptor that was built on a different kind of grid. And then you can even do things as go to more extreme or more, let's say, complicated ways to split your paths into individual areas. And then you start getting the actual histograms or characteristics of your paths inside its single area. So this is more or less a generic way of getting a descriptor. And then you can see that you can arbitrarily increase the complexity of how you discretize your angles, how you represent your grid inside your paths and things like that. So this is another case, Daisy, where it's again a way to aggregate the gradients from your paths. And then you can see that if you imagine these rectangular areas being the paths, then you start by overlaying some Gaussians, which have the sizes that you see here. So this is to keep in mind that there are lots of different ways to just aggregate your responses into different methods to get the global descriptor. Once more, we can see here, this is a more complex design in terms of getting the individual grid, although they're not grid anymore, the individual areas, let's say, of the paths that you aggregate to specific parts of the histogram. So this is LEOP, which works by dividing the paths region into individual subregions, and then by converting its bin into a fixed size histogram representation. And then you multiply the number of bins by the number of elements per bin, and this is how you have your final descriptor size. So you can see how this could help with extreme rotations, because in theory, the region division should not change when you do extreme rotations. So in the end, you'll end up with the same histogram, although it's not always the case in the real applications. So one other example I want to mention, just to show that it's not always the same pipeline, which is you split your paths into areas and then you aggregate characteristics from paths to individual histogram elements. This is an example of Lucid, which was a descriptor published in NIPS, I think, 2012, which is very interesting because it's completely different than what we've seen before. So the key idea with Lucid is you have, let's say you have an RGB paths, then you can split it into the three channels, R, G, and B, and then you just flatten the paths into a vector. And then what you do is you sort this vector, and then you also have the arg sort, which is how the indices change in order to have a sorted array. And then what the author said here is, why don't we just use the arg sort as the descriptor? So the key idea is that if you, let's say you change the intensity of the paths, then the sorting is the same, right? So if you occlude something, then maybe some of the sorting, part of the sorting will be the same. And this actually works quite well in terms of an actual real world application. It's not heavily used anymore, but still this is a good motivation to just think that there could be other designs. So it doesn't always have to be, you split the paths into regions and then you do individual histograms. Another area that is not that much commonly used, but it's important because it shows improvements, is aggregation over scales and viewpoints. So the idea is you have one path, then you don't have to constrain yourself into only this representation of this one path. You can just change the scale a bit and then aggregate all of the responses into a big into a descriptor in the end. Or you can rotate the paths a bit and then you can again aggregate all the responses. The price you have to pay is obviously a higher computational cost, because if you, let's say, rotate the paths 10 times, then you need to run your method 10 times. So that's probably a much, much slower one than just doing it once. But the important thing is that these methods have been shown to be very, very powerful in terms of performance boost. So this is one such case, which is a SIFT. If you see here, you have your original image, which is A, and you want to match it with another image, which is B. And then what this paper did is you start by introducing manual affine wraps on your original image, and the same for A and B, and then you match everything to everything. This is, of course, very, very computationally expensive, but they saw that this can lead to much improved results. Similar idea, but on the scale space in terms of changing the changing factor and not the orientation or the translation that is changed in the affine case from a SIFT. This is DSP SIFT, where the idea is you, instead of getting one descriptor from one scale, you just get 10 scales, and then in the end you aggregate everything together. Again, it's slower because you need to run it in more cases. But again, this shows that you can improve the results quite a bit by doing this. So another thing to keep in mind is that you can, if you have a base method, you can probably get a much better method by either aggregating in scale space or by introducing some affine deformations and then aggregating a final descriptor based on everything in the end. But it will mean a much higher computational cost in the end. So up to now, all the methods we discussed were either floating point or integer descriptors, which means that if you have a final vector in the end, then the values that you have are either integers or floating points. But the need to get much bigger speeds and much lower memory led to a development of the so-called binary descriptors. So these are descriptors that have either 0 or 1 in their values. And this was driven, for example, by some hardware requirements. So there was some Intel processors that had a very fast way to do XOR operations into binary if you have a way to represent your data in a binary way. And this is one such case that you could probably make your matching like 10 times faster just by using this. So in the first and easiest way to do this is you can start by extracting your original descriptor, which in the case of LDA has, which is this this image described here, shown here. This was you just start from your original SIFT descriptor. You represent it as a point in the original n-dimensional space, and then you start adding hyperplanes in this space. And then if your point is on the left side, basically the inner product is higher than 0, then you put 1 in the end. If it's lower than 0, then you put 0. So by, for example, increasing the lines or hyperplanes you include in your computation, then you increase or decrease the final size of your binary descriptor. But this, of course, is not super efficient because you need to first compute SIFT and then do all your inner products. So it's not ideal. So some authors, like the authors of Brief, try to think of ways to do it directly, similar things on the image paths. So in this case, if you think this rectangle as the image paths, what the authors of Brief did is they just manually and randomly created lots of tests, which are defined as, let's say, two pixels from the path connected, as you see here with lines. And the idea is if the top, let's say, if the top pixel has higher intensity than the bottom, then you put 1 in the final descriptor. If it's the inverse, then you put 0. And then by adding more and more such tests, then you can increase your descriptor size. And this is, as you can imagine, very, very fast because you don't even need access to the whole of the image. You can just focus on very specific intensities in specific pixels, and you can make a very fast implementation of this. So they demoed this on mobile phones and back in, I think, 2010 or something. So back then it was a very efficient way to do stuff on mobile phones. So Brief is not the only binary descriptor, but due to time limitations, this is the only one I'm going to mention. So another important aspect is learning-based methods. So everything that we have said up to now does not include any learning on data. So these are all design methods based on filters or some intensity tests. So, but from 2005 and on, more and more machine learning was utilized. And one such case, again, that builds on top of SIFT to do something else is the PCA SIFT. So the idea is, again, quite simple if someone knows how PCA works. So you have your SIFT descriptors, and then you want to reduce their dimensions to something from 128 to something lower, for example, 20 or 30. And the way to do this is you can just form a data matrix, get the PCA, and then from this matrix, for example, the matrix that has the eigenvectors, you can keep only the first n columns to reduce your size of the descriptor. And then if you're lucky, then you also get rid of some of the dimensions that represented very high noise. So you might end up with a better descriptor in the end, although you move to less dimensions. This is one case of the such PCA components. So the top 5 figures you see, the blue lines, are the individual eigenvectors for each of the. So this is the first, the second, and so on, from a SIFT method. That's why it goes from 0 to 1 to 8 if you see the x-axis. So you can see that they're different. So as you move on later on towards the eigenvectors, you represent different changes in your sigma. And then if you see the bottom row, this represents the same thing, but when you use the original patches and not the SIFT representation. So this makes it very nice because it's very visible, the kind of things that PCA projections will focus on. So you see that they start from very rough things like edges or changes in intensity from bottom left to from top left to bottom right. There's some circular aspects there, and then it goes to some higher level elements later on the right. But only using PCA is not ideal, again, because you don't have any information about the labels. So you don't know, you're projecting down in a space that has no understanding about what is the same or what is not the same, which is something that's very clearly defined in the case of descriptors. So in this case, in a paper, I think again, close to 2009, the authors try to incorporate LDA kind of framework, which has the knowledge about if something is similar or not, if two things are the same or not. So by using this, you can instead focus on creating two data matrices, one representing the differences between similar key points and the other differences between dissimilar key points, and then you can start building on top of that. And then there's a way to analytically solve for this and to get the projection matrix that again comes from the eigenvectors, if you sort by their eigenvalues, of course, in the end. So if we do the same experiment again here with the patches, we can see you can ignore the P and U. They're the same process, but with slightly different details. So you can compare P with PCA, so the first row with the last one. And then you can see that adding the label information into the machine learning process leads to much more localized responses in terms of filters in the end, which we can think again, this as a set of filters that you can use on top of the image or the paths. So this again has shown that it works much better than getting only the PCA of the image. So this is again another case of a successful use of machine learning into the local descriptor pipeline. And again, there are many methods in between, but I just want to focus on the latest one before the deep learning period started, which is something called learning local feature descriptors using convex optimization. And that was from Oxford. And the idea here is that you can formulate your whole problem in a way that it has a convex, let's say, it has a global optimum due to the fact that it's a convex optimization. So the authors formulated the path description in a way that in the end they could prove that given the assumptions they made in the end, this is the optimal way to generate the descriptor for these paths. And then if you see, it actually looks quite a bit like the DAISY case we saw before, which is if you're close to the center of the paths, then you need to use smaller size Gaussians, and then the more you go out, the machine learning method is using a higher size of Gaussians. So the interesting thing here is, as we said, this is the optimal descriptor for the given, let's say, assumptions in the end. And again, this proved state of the art comparing to every other machine learning method in the end. And this showed once more how important the learning utilizing of data is into this process. So this was just a couple of years before the whole thing started with deep learning. So, but actually it's, I think this was probably 2010. And the interesting thing is that up to then, no one was using deep learning in descriptors, although some other people had showed good results even before the ImageNet challenge was won in 2012. So even 2005, some people were working on deep learning. And interestingly, there was some early work in descriptors too, even before the big bang of deep learning. So in 2008, there was this paper that was using deep learning to learn descriptors, and it was doing that by again using synthetic deformations of the original image and then training a method to understand that, what is the same and what is not the same. And this was from 2008, as I said, but this was not followed, which is very interesting because this was, as I said, 2008, and it was probably 7 or 8 years before the people in the descriptor research area started focusing on deep learning, which is very interesting. So that shows that if you're first, you're not always the most successful because somehow the paper might get lost, or people, just didn't know about this, I guess. And the interesting thing I want to point out here is that as you can remember, we have focused on the convexity, which shows the optimal way to build your descriptor. And then on the other hand, we get the new deep learning methods starting to emerge, I mean, publicly and in the whole community. So the first interesting experiments that showed, I think at least this is when most of the people from the descriptor side realized that, oh, this is something we need to focus on, is when people saw that you can get a pre-trained network on ImageNet. So this has only seen I mean, it's a lot of images, but I mean, it was trained to identify what is shown in each image. So a standard classification problem. And what was shown was that if you remove the last layers and then you use the features from this and then you use them to describe patches or local areas of the image, then you're much better than SIFT. So if you, and this was shown in the paper I'm showing here, the reference. So as you can imagine, this was pretty important because it showed that there's the representations that are learned internally in deep networks, even though they have been learned for something else, they're still very, very useful for image matching. And again, if you can remember all the possible ways to get descriptors I've shown, go into very detailed grids, make some very complicated and fancy ways to define your problem, and then have a convex formulation that leads to an actual global minimum. Then again, all these things do not matter because in the end, if you just remove the fully connected layer of an ImageNet trained network, and then you just use it on local parts of the image, then you get much better results. And as you can imagine, this led to people focusing more and more on deep learning methods because it was clear that this is the way forward. In this case, most of the work was based on ways to learn from data from a set of input patches using a neural network, and then having some kind of ground truth, which is either if these two patches are matching or non-matching, then you could start building methods on top of that that are trained based on the data you give to the network. So probably the most successful case of deep learning descriptor that focused on training from patches was this paper from 2015, CVPR, that showed that you can use a standard Siamese network, which is actually very similar to the paper from 2008 I showed before, but now it works individually in patches. And also what this paper did that the other paper didn't do was it went very deep into architectures and ways to train, and then it showed much better performance. So that's why I said it's probably not always important to be the first when you're doing something, because Deep Compare actually focused on how do you represent the path, how do you represent the descriptor in the end. Do you need to use Euclidean distance? Do you need, let's say, to use a specialized layer to do matching in the end? And this, while again is very similar to this, it was much better in the sense that it actually proved that it worked, and it had a very thorough investigation. So another way to do training instead of using Siamese networks is to utilize triplets. So this means that you have 3 copies of the network in terms instead of 2, and your loss is just based on the fact that you have a triplet where the first 2 things represent the same thing, and the last part is different. So basically, your training is based on the fact that if the descriptors you get from the first 2 are more similar than the descriptors you get from the first and the third, then you don't need to update your network. If it's not, then you need to update the network in the direction that is defined by the gradients that you accumulate. Then people started building again more and more complex things on top of the networks, and one such case was L2Net that combined a very simple architecture with a few convolutional layers, 5 or 6 if I remember, and with 3 complex losses. So instead of having only one loss, which was the distance loss, the authors of L2Net focused on different things, such as the whole matrix similarity. So if you have a mini batch, then you utilize all the possible distances, not only individual pairs. Then it also had a compactness loss, which has to do with decorrelating individual columns of the descriptor if you think of the data matrix. So the idea is that each individual elements or individual numbers in your descriptor should be decorrelated with each other. And it also had some intermediate feature maps losses, which is you add losses in other areas of the network too. And this actually showed quite good performance. And the other good thing that came with this is that, as the author showed, then the range of the values for each individual descriptor dimension in the end followed a nice normal distribution. So that means that you can get a binary descriptor just by getting the sign of the output. So if you set your threshold exactly at the mean of the Gaussian, then if it's higher, then you put 1. If it's lower, then you put 0. So you can also have a nice binary descriptor in the end without doing any extra training. And if you see the original numbers from the paper that are also pasted here, then it performs quite well in terms of the final result. So on top of that, actually, this paper, HardNet, so that you don't need all these fancy losses, because if you have a way to have a better way to build your triplets in the way that you use your hard negatives, which are the confusing aspects, the confusing patches during your training process. So if you have a way to deal with them, then you can use a standard, more standard, let's say, triplet loss, but because you build the triplets in a nice way by focusing on very confusing very confusing negatives for your triplet, then you can have a much better training and in the end get much better results. So you can see again here the results that how important the HardNet is for the hard negative mining is compared to just not doing it. And the other nice thing here, if I'm not mistaken, the plus here means augmentation. So I think the authors did lots of experiments about how much having augmentation improves your results. And I think after this, it's quite common for the methods to train with more augmentations on the patch level. So again, you can see that we can keep building more and more complicated losses. And this is another case of such a loss, which is SOSNet from last year's CVPR. In this case, there's on top of the first order similarity loss, which is a loss that's based on the distances between patches. There's also a second order similarity loss, which is a loss based on the difference between distances between patches. So the idea here is when you have, let's say, your patches before the training, they're all over your descriptor space, so they don't have any meaningful relationship with each other. So these two you see are closer, although this is clearly the same as this. So the idea that the second order similarity is that you also optimize differences between the distances. So if this path is that far away from this path, then this path should also be similarly far away from these paths, because these two are in the same class and these two are in the same class. And again, there are some results in the paper that show that adding this second order consistency improves things. And this is one example where you can see how much it improves things in terms of map building, in terms of an SFM pipeline that we mentioned in the beginning. So this is a map built with a standard triplet loss, and then you can see that it's broken. So it's a red dot here is a camera position, so it's broken because this is supposed to be someone walking down the road. And then by adding the second order consistency, then you get to a much better map in the end. So just to sum up before we move on to the more modern, not the classical pipeline, which are new ways to do the whole matching process. So this is the current status of the classical pipeline, right? So you can have pretty nice matches between images. They can handle different difficult cases. They can handle very extreme viewpoint changes. But there's one thing they cannot handle at all, which is extreme cases with lots of people and lots of weird things on the background or in the foreground that confuse the detectors and the descriptors. This is one case of trying to apply, I think it's SOSNet, to a very difficult pair of images, which is day and night. And then you see on the right image, there are lots of people standing here. So you see that the results are completely messy because you get lots of key points on the people which do not even exist on the left image, right? So the scene changed a lot. So it's very, very confusing for the classical pipeline, because probably most of the key points that come in this classical pipeline, especially in the detect case, so you see that most of them will have completely changed between the day and the night scene. So the recent years, people have been trying to find a replacement, especially focusing on different cases like this. And the idea is you either get rid of the whole pipeline or you just replace some parts. So the limits of the classical pipeline are what I mentioned, especially very difficult cases where key points and patches are not the ideal case to describe your image anymore. And that's why the recent work has been focused on trying to replace either the whole pipeline or parts of it. So this is what we call modern methods here. So, and also recently, also in this year's CVPR, there's some papers focusing on even changing the matching method, which is you don't focus anymore on having a distance matrix and then getting the argmeans of this, but you find new ways to do matching between images. So one such case of a modern pipeline was LIFT that basically replaced every part of the classical pipeline with the equivalent or relaxed version in a differentiable way in a deep network. So the detector was based on a score map, and then soft argmax, and then cropping, and then orientation, if I remember, was based on spatial transformers. And in the end, this whole pipeline was trained in many stages because of how complicated it was. And the orientation or the scale changes and the descriptor changes were trained in the end in this kind of way that this complicated diagram you can see it here. And then in the end, during test time, you have an image, you can have a pyramid, you get your scores, you get your key points, you crop your patches, and then you get your orientations, and then you get your descriptors in the end. So you see that it has equivalent with every part of the classical pipeline, but some parts are changed by deep learning equivalence. Similar but more advanced way of doing that was the LFNet paper that again had some pretty complicated training and warping of the score maps and replacing specific parts of the pipeline with deep learning equivalents. And this actually started showing still wasn't as good as the classical pipeline for, especially for some cases, but everything became more and more promising in the end. Another important area is, as I said, learning correspondences. So you have your descriptors; you can get them with any method you have available. But how do you do matching is another thing. So you can learn a network that does exactly that, which is learning to find good correspondences. A paper from a couple of years ago. Then people started doing an end-to-end pipeline, and then tried to find ways to learn both detector and descriptor at the same time without cropping patches, for example, like the previous two cases. So one such case is a superpoint that the authors focused on ways to generate pseudo ground truth interresponse by doing some kind of synthetic data augmentation. And then in the end, they try to have one key point loss, one descriptor loss, and in the end, train them all together to do a joint detector and descriptor method. So in the end, you have an input and a common encoder, and then you have two decoders, one for points and one for descriptors. Another recent method, just to show you that, again, you can think differently in terms of how you present points and do actual matching, is this paper, I think probably from 2019, if I remember correctly, that focused on doing matching just by using the individual feature maps of a network. And then by identifying specific places in this feature map, and then finding the maxima across all the feature maps, you could do local matching like this. So you don't even need to have the classical definition of what a key point and the descriptor is to do matching. In the same sense, people started exploring doing this with some attention scores. So if you learn, let's say, a method to do global matching, image retrieval, then you can start using the attention scores that come up from this, and then you can probably connect the attention, high levels of attention, with interesting points, because if the network gave high level of attentions there, then it's probably something interesting for you to identify the landmark. And then you can go back and use this for local matching, although it was never trained for this. Another recent paper is D2Net, which does something similar to the things we said before with the scale spaces and the finding maxima and minima, but it does it on the feature maps that are outputted from a network. And then there's also some training on top of that, but the important idea here is that you can somehow use a standard feature extractor, even ImageNet, and then you can use the features that come up that come after this, both for identifying key points and descriptors, and then you can use them to do local matching. Another recent paper focuses on doing that exactly, but without having any point-to-point correspondences. So the idea here is similar to the Delph idea before, which is you learn a network to do global matching, to do retrieval, and then you can somehow go back and do individual point matching just based on the retrieval. And then just to show you an example of what you can do with pre-trained ResNet or D2Net is you can start getting some at least pretty good matches in these difficult images I showed before compared to the standard classical pipelines, right? So if you see, you start getting some reasonable matches, which is, if you remember, nothing compared to what was there before. So this is the last, I think, paper I want to mention, because it's from this year's CVPR, which is Superglue, and it's somewhat related to the D2Net or the superpoint ideas. But now what you have is a full network that also does a new way to do matching in the end. So in the end, you don't just get the descriptor and then you do your distance matrix to get the matches, but you have a graph neural network in the end that finds the strong matches for you. And then you have an optimizer that does the whole thing and optimizes the whole thing, right? So as you can imagine, if you have an optimal matching layer, then this is much better in terms of the final results. And this paper is presented in this year's CVPR for people who are interested. And just briefly want to mention a couple of other methods that are not exactly related to matching, but they can be used for the same thing, which is, for example, building maps. One such thing is, one such case is Daemon, which gets a pair of images and recovers rotation and translation of camera. Another one is PoseNet, where you don't even have features anymore. You just get one image and then you can recover the camera pose directly. And the recent one is also local sync coordinates. Is for each point in the image, you directly predict the original XYZ position in the world. So you don't need to do matching in the classical sense that you have two images and then you try to recover camera poses. And lastly, to motivate also the Dimitros talk, which is coming up after this, is how good are modern methods. So as we have seen, this is what you get when you try to run the classical pipeline, a very challenging result. And this is what you get when you try to run a modern method that's based on end-to-end training, based on feature maps from networks. So you can see that it actually does very, very good for this kind of example. And this is a slide I borrowed from the Dimitros talk, which is, they're not always better, of course. So Superpoint and D2Net are two very recent modern cases. And then you see that they somehow find a pretty nice, especially Superpoint, nice homography. D2Net not that much, but then DOG and HardNet, which is, although HardNet is a deep learning descriptor, it's still the classical pipeline because you first find key points and then you find descriptors. So the last row you see, it's much better. So this is just an illustration, I guess, that is not always the best to do end-to-end, or at least that the modern methods are not on par with the classical pipeline in every step of the way. So there's some state-of-the-art and related and future challenging open questions, which, for example, do we even need local patches anymore? Or how can we change the whole matching paradigm? For example, like the super glue paper discusses, with completely getting rid of the distance matrix in the end and adding a graph convolutional network. So another quite interesting question is, how can we relate attention to detectors? So for example, similar to the Delph motivation from the Delph paper. And another big, I guess, question is end-to-end learning always better for every stage of the pipeline, or can we just plug and play between classical and more modern methods? And that's it from me. So this was the overview of the classical and the end-to-end methods. And the next part of the tutorial is Dimitros talk, who will talk about how do you go actually from the paper and all these nice methods to practice, which is when you want to examine your methods in a large scale scenario, what kind of challenges you have. And I'm pretty sure Dimitros can explain more this whole idea. So
hi,
yeah.
Could you please stop share your screen and so Edgar or Vasileos, please stop sharing your screen and allow me to do it.
I stopped sharing, so it should work now.
No, so host disable participant screen sharing. So can you click on me and allow this?
I made you a host.
Yes,
so now
great.
You to do.
Thanks. So hi, everyone. I'm going to present a huge, gigantic benchmarking effort, which is joint work with a lot of lab from Czech Technical University, from EPFL, University of Victoria, Google, and so on. So I will cover local features, how are they working, and maybe you should not only look for the local features, but some other things are also important. So let's start. And first, let's start again with this thing, like what are the main parts of the local feature matching. There you have two images, you detect some key points, then you estimate your measurement region, which means that you're going to describe, because key point is key point, X and Y. But in order to match them by some image content, we need to define this part of image. Then we could also normalize it, which means that we need to select orientation, or if it's done by photographer, you can do just upright thing, or you can also estimate some shape of local feature. Then you describe local features by any kind of descriptor, SIFT, hardnet, or whatever. Then you do matching and filtering, and this is very important part, that matching is just L2 or Hamming distance in the descriptor space. So you go for nearest neighbor, and then you need to filter out your unreliable descriptors, because if you are looking for the first nearest neighbor, you would always have one, like be it good or bad. So because you haven't asked algorithm for there is no match. And mention filtering is exactly this filtering. So we need to have only good descriptors, good correspondences. And then we go to geometric verification, assuming that we have some model of the scene.
Sorry to interrupt. I think you need to
Yes?
swap your screens, because now we're seeing both the next slide, the current and the next slide. Or if you want you want to do it like that.
So sorry.
Yeah, there's this swap screen somewhere.
Screen sharing. So what do you see now? Is it the same as before?
Yes, I think so. So you should see a button, I think, on PowerPoint that says swap screen.
Okay, so what now?
Yeah, now it works. Thanks.
Now it works, great. And then you have of the scene, which means that you have images taken by two cameras, or you have some taken photo of planar scene, or you do medical image registration. That means that some elastic deformation can appear, and so on. And then if your nice good correspondences here, which are according to this geometrical model. And here is a toy example of how would you do with Python and OpenCV, just to show you. So you first create some detectors and descriptors, then you match them, and you find homography, because this is planar scene, and then we draw matches. And this is toy example is available on GitHub and Jupyter Notebook, so one can play. And this is what we have as a result. So yellow guys are our correspondences, which are consistent with our homography model, estimated one, which is blue one. And the ground truth green, correct one, is green. And you can see that they're not exactly correct, but pretty close. So now let's that was a toy example, and now I'll talk about benchmarking and like more large scale example, and then we'll show some examples on both. When you do this local feature matching, it's kind of hard to get a ground truth because or some good metric. Why? The problem with the current lots of benchmark features detectors and descriptors is that they are just focusing on is a thing like detector repeatability, how like reliably you detect your features, for example, or how you, or on descriptor performance. And the problem is that some benchmark can say, okay, this descriptor is 2 times better. Would your end task be 2 times better? Results, probably not. And how, you have no idea. So then there was like 2 years effort for doing this benchmark, and we spoke about on the Friday workshop on image matching, and there is an image matching competition which associated with this, so I invite you everyone there. And so how it works. Imagine you have a bunch of images depicting the same scene, like Eiffel Tower, some Sacré-Cœur, or some other landmark. You can fit into some structure from motion thing to get 3D reconstruction. Pretty good when you have dense sampling, which means that your camera pose, your photographers taken from different places, and these are like nearby. On this large scale 3D model, you can get your so-called ground truth. Not so-called because it is by structure from motion. Nobody was measuring that with laser scanner and so on. And then in next slide, I'll show, can we trust this ground truth or not? Answer is yes, we can. From this full data set, we can create some image subset up to just 2 images. And then we can do this image matching pipeline. You go through and you got your camera pose. So feature extraction, matching, pre-filtering, and then you can compare this camera pose, which you estimated just from 2 images, to the camera pose, which was estimated from thousands of images, which is very, very precise. And then you can say, okay, if the pose error is small, probably all my image matching pipeline working very well. If not, then not. The data set is phototourism. It is created by subsampling just relevant images from the Yahoo Creative Commons and split in 26 scenes. And you can see like images like this fit in the column and get this pretty neat reconstruction of the Trevi fountain in Rome. And this is basis of the image matching competition. So, and here are examples of the images and the depth maps, clean depth maps which we got. And what's important that these depth maps not used for the detectors and descriptor comparison because they still can be noisy. What is used is camera pose. And also one could say, okay, but if we go like full circle around some object, that some images can have like no co-visible part. That's why it ensures that there are some 3D points which project to both images, and this convex hull bounding box of in each image containing them, and we can get the scale of this bounding box compared to whole image. And if it's not too small, then we can use this image for benchmarking. And what is the metric? Metric is the actually end pose, which probably if you're doing image matching, you're interested in some kind of camera pose or 3D reconstruction. And the goal for 3D construction is to get as full, as dense, and as precise as possible. So we don't measure any like denseness of the point cloud resulting. It's probably too hard so far, but we can measure the camera pose accuracy. So we estimate fundamental metrics. Then by known camera intrinsic parameters, we can recover the essential metrics, camera pose, decompose this camera pose to the rotation and translation components. And because our reconstruction is scaleless, we have no idea if this Trevi Fontaine is 2 meters or 2 kilometers, but everything is like up to scale. So we measure on the angle error at 10 degrees accuracy, which means that if camera pose difference are in this threshold, then we think that is correct. And if it's below this threshold, then it's incorrect. And this is upper threshold. We have set of thresholds from 1 degree to 10 degrees. And can we trust Kornia ground truth? Because Kornia uses SIFT detector and descriptor to get initial estimates and then make some densification and so on. And the short answer is yes, we can. The idea of the whole paper is that we can whole method of benchmarking, that if we have more images, then the error and stability becomes bigger and better, and the error and camera pose difference becomes smaller and smaller. To verify this, we did the following experiment. So we feed different local features into Kornia reconstruction pipeline and compare the overall accuracy of these camera poses compared to our SIFT reconstruction with all images. And we also vary number of images. And as you can see that with increasing number of images, the mean error and the median error decreases. And this is actually pretty consistent for all local features except superpoint, which is not as precise as R2D2 or SIFT. But I think it is not because but because it was trained to output just 2K key points, while R2D2 or SIFT can output 8K, 10K, which results in much denser and more precise point cloud. And as you can see that mean error is less than 1 degree, and we measure accuracy at 10 degree threshold, we can say that our ground truth is precise enough to do any comparison. And I would like to start not from local features, but from something which is often overlooked and can be basically can kill your performance very easily, even if you have the best possible local feature in the world. So if you fail any of these steps of the pipeline, then you fail everything. Okay, so if you're not familiar with RANSAC, please check our yesterday tutorial. Videos are not yet there, but slides are. So it's nice introduction to RANSAC from the beginning of the times to the the very latest modern and deep learned variants. So, and a year ago, I had a Twitter poll asking which RANSAC do you use? And most of people use OpenCV, some use USAC, and is it good or not? And the answer is no. Here is, we feed the same local features with the same optimal matching threshold, and then use different RANSAC variants to measure this camera pose accuracy. And as you can see, the OpenCV RANSAC is very, very, very bad. It's almost 2 times worse, maybe not 2 times, 1.5 times worse than some modern versions like DegenSAC, MaxSAC, or GC-RANSAC. And list medians is also a bad idea to use because it's not robust enough. And SKY image, it looks like that is fine, but the problem is that it's implemented in pure Python. It's 2 orders of magnitude slower for the same number of iterations. And this benchmark was done just recently, a couple of weeks ago. And you can see that the best benchmark is RANSAC is GC RANSAC, especially when combined with different other methods. And in the paper I'm mostly describing what by Ian et al. Then actually GC RANSAC is not as good, and the answer is because it contains additional hyperparameters which needs to be tuned. If you don't tune your all hyperparameters on some training or validation set, or just on two couple of images you have just in case, then your performance is bad. And you can see that SK image, so this is time in seconds, this is performance, so SK image is very slow, and the OpenCV RANSAC is bad, and these are modern RANSACs. Okay, moreover, you need also to tune your RANSAC reprojection threshold for each feature do you use, because the optimal value which are shown in these dots or markers can be very, very different. For example, sorry, you cannot see the scales, but so here is this 1 pixel and this is 10 pixels. And you can see that for some RANSACs or images, it's near the 10 pixels optimal threshold, and for another 0.5 pixels. Oh, okay, here they are. This is for different RANSACs, so you can see that first curves are different, that some RANSACs are more forgiving and others are less forgiving, and for each local feature, you need to pick the different threshold, otherwise you might have very inferior results. And don't try to catch which local feature is which. I'll go to this later and describe in details. And it's just to show you that these optimal thresholds vary really greatly. So if you haven't tuned the RANSAC, you probably don't have a good performance, and don't trust defaults. OpenCV defaults, just in addition to even tuned OpenCV RANSAC is bad for F, then its defaults is even worse. I think so it's somewhere here, it's like 0.40 something, and say instead of what you can have from it 0.52. It's MAA things. So use GC RANSAC, RANSAC, or DegenSAC. They are all available on GitHub with Python bindings. And for DegenSAC, you can just install it with pip install. And also don't use USAC. It's bad as well. Matching and filtering. This is all overlook things, especially now when people say, okay, we use deep descriptors, we don't need any like these old filtering methods, and then you have very bad results. Don't do this. So, and I'm going to overuse like simplest handcrafted matching strategies. So first is that your match features from image 1 to image 2, and you just pick the nearest neighbor for each pick. So first, you can see that there are two problems with it. The first problem is that you have different features from image A matching the same feature in image B. And of course, they both cannot be true. One of them is correct and the other is incorrect. And if they would be together sampled for RANSAC, you are in trouble. And another thing that this is kind of asymmetric. So you have different results if you match from image B to image A. So, and if you fill into OpenCV RANSAC, by the way, for homography, it's quite good. Unlike for the fundamental metrics, you will really, really fail. Just because of this problem I just described, for that many features can match one another image. Okay, then you can ask for cross consistency, which means that when you match features, you need to image A matching image feature from image B and vice versa. Therefore, we kill these guys and we have only this green one. Fine. It's still not like good enough. What we can do, we can actually estimate how reliable is each match by first or second nearest neighbor ratio proposed by Lowe in SIFT paper. And basically the idea is that you find two nearest neighbor instead of one, and then what you do, you compare the distances to them. If they are too close, that means that probably the match was done just by random chance, it's not good, unreliable, and we throw it away, and we just have less matches. So does it work? Yes. And this is why you should, the thing which you should do for almost all features, regardless of they learned or handcrafted. Then you can upgrade this a bit and use first geometrically inconsistent nearest neighbor. What does it mean? If you have features which can detect multiple orientations, like here on symmetric objects, or you just detect some features which are really nearby, as here, and then your second nearest neighbor would be almost the same patch as the first nearest neighbor, and you can think that is like they are unreliable, you throw them away, although they actually are both equally good. What you can do that you can ask methods that you only accept second nearest neighbor as second nearest neighbor if it's far enough from the first nearest neighbor in the image, not in descriptor space, but it's like here. And these are these yellow guys, and this improves results a bit. You can have more correspondences and a bit better model with such thing. And of course, you can do the things symmetrically, that you do it from one image to another, then from another image to the original one, and you keep only cross-consistent methods, and these work the best. Now, the matching threshold, which I mentioned here, that this is 0.8 as in SIFT paper. So this is a ratio, like threshold on ratio, where you decide to keep feature or to discard it. It needs to be tuned per local feature and like descriptor and detector. And if you check the graph, the only method which is like better with just nearest neighbor matching is D2net, and in stereo. And for the rest, okay, not for stereo, for multi-view as well. So the other methods are greatly benefiting from the such kind of filtering. The same holds true even for binary descriptors, and for binary descriptors, it's commonly used Hamming distance threshold, which is just descriptor distance. So if your distance to first nearest neighbor is less than this threshold, you keep match. If more, you discard it. But it turns out that it's better to use this first to second nearest neighbor ratio for the binary descriptors as well, and you have can have better results. So this, as you can see, that these red guys are better than blue always. What about this for geometrically inconsistent? So turns out that it does not really increase your accuracy, unfortunately, although sometimes it does. But what it does is make your like safe area where you can miss your optimal thing because you're doing grid search onto coarse grid or whatever. So this third geometrically inconsistent makes the like optimal parameters area like wider. And what about deep learning methods, which were vast and mentioned in previous talk? So deep learning methods, and if you believe what is stated in paper that with such filtering methods you don't need even RANSAC, well, it's not true, because good RANSAC with classical threshold is still better. But if you combine the deep learned things with a RANSAC, you have like pretty decent boost in the accuracy. And here is benchmark, which we done specifically for RANSAC tutorial. Is that we asked people, authors of these methods, to train exactly on correspondences which we send them. So all the methods were trained on exactly the same correspondences, exactly the same data. So one cannot say that one is better just because they have better data or more data. No, well, this is kind of fair comparison. Of course, that some method would benefit from more data that we gave them, and we gave like 1.5 million image pairs, and maybe it's 500 or 1,000 correspondences each. So maybe it's not enough for some method, but for those which are enough, so you can see that the OANET and ACNI, I think is presented on this CVPR, works the best. So deep learning methods are not replacement for the RANSAC, despite they are often sold like this. For matching, they are a replacement for the correspondences filtering method, like first to second nearest neighbor ratio. And except for the superglue, I think it will be presented on lots of workshops on this CVPR and also its oral paper. So, and it improves greatly local feature matching. And in this competition, so this first three entries are variants of the superglue, and here it is the best non-superglue submission. You can see that the difference is huge, but it takes the much richer input than the other method. It takes not only just correspondences, but all the descriptors, all the key points, and run optimal matching on the top of additionally learned descriptors. You can say that superglue learns image pair specific descriptors, which incorporate all information which you have from two images. And this is no surprise that it works much better than something which was just trained for the patch things and never know any context and so on. I urge you to read the paper and watch the superglue talk. Now, about descriptors. So this was introduced by Vasileos, and its variants, like modern variant SOSNet, is one of the top performing things. And now let's go to these local features. We have tested classical methods and learned methods. So among the classical, we have SIFT, root SIFT, surf, a case, orb, and freak, which are the binary descriptors and detectors as well. So these red guys are 2K features budget, and blue are with 8K features. And what you can see is that all binary descriptors are actually quite much worse than which is expected because they are much faster. And all these guys from our L2Net, and that's L2Net, HardNet, GeoDes, ContextDes, SOSNet, log-polar descriptors, they run on top of OpenCV SIFT key points, which are difference of Gaussian, just simple blob detector. And then, so we crop patches, and here they are. They are pretty good, but if you can compare them to the root SIFT, which is like best gold standard handcrafted descriptor, that you can see that difference is significant, but not actually huge. Like it's up to 10 percentage point, often less. And the end-to-end learned models like Superpoint, R2D2, especially LFNet and D2Net, they are not working really well. R2D2 works really well, but still worse than just simple handcrafted SIFT detector. So and this is like tables with numbers, and you can just download slides and like check it probably later. So the best descriptor for the two-view matching is SOSNet, and it's very closely followed by HardNet. What's interesting is that it's not always when you have more data, you have better results. This AMOS plus HardNet is trained on 3 data sets, like Brown dataset, HPatches dataset, and AMOS dataset. While there's this HardNet and SOSNet, we were trained on just one single sequence of the Brown dataset. And it turns out it's better. So we probably don't know yet how to use more data for when you train for local descriptors. So it's not always that you need a very, very large scale data. Sometimes it's enough to have just a bit. For the 2K track, which means that you have just only 2000 features, then KeyNet detector performs pretty well with HardNet. We haven't tested it with other descriptors. Suggest to use HardNet, but probably with SOSNet it would be a bit better. So it's the best choice for the thing. And KeyNet is a learned detector with handcrafted components. Maybe that's why it's so good. Because for the low-level things, like to be very, very precise, the handcrafted optimal filters are kind of still important. Doc and HardNet are state-of-the-art for multi-view, and multi-view means that you have more than 2 images, like 5, and there you matching everything to everything, and then you build a 3D reconstruction with CallMap, and then just compare the results to the large-scale 3D reconstruction. It's worth mentioning that the difference between methods is a bit smaller here, probably because that once you have multiple observations, it's much easier to get a camera pose right than if you have just 2 images. So HardNet is the best. Context Desk, which is a HardNet plus some variant of the incorporating key point features, is second. And you can see that DetoNet successfully matched the most of 3D reconstructions, like outputted something, but this something was not precise enough. KeyNet and HardNet is the best for the multi-view 2K reconstruction. So, and R2D2 is runner-up, so this is where it works. It's robust enough as a descriptor and detector, and it's better than this DOG things. So because when you have less key, and you probably would like to be more robust, so you would like to detect the same features, even if it comes at the cost of being a bit less precise. While when you doing 8K, you can actually just brute forcefully spam lots of features, and this would be working very well with precise features like DOG. But when the features are limited, then actually R2D2 and KeyNet works better because they're more robust, and SuperPoints is actually working pretty well as well. Measurement region selector, feature orientation. So when you're matching some images, they can be arbitrarily rotated. At least what the people believed is like at the beginning of computer vision, that computer vision should be able to match images regardless as they are rotated or not, which is sometimes true, but sometimes just a photographer makes sure that it's we don't photo like this. We usually photo like vertical or horizontal, and in most smartphones you have some EXIF data to correctly rotate this. So yet sometimes it's not the case, and we would like to detect some orientation for the features, and you can do it quite easily with some handcrafted things like dominant direction of the gradient. This is 2 example. This is from black to, or from dark to light things, and if you rotate this, it rotates as well. Or you can train a neural network to output your orientation, and just optimizing for the best matchability or repeatability of such orientation. And it works. Learned orientation gives you some improvement over the SIFT handcrafted one. But if you can rely on photographer to keep the orientation, then it's better to just switch it off, because it's very good but not perfect. And here for upright variant can be always perfect. If it's done by photographer. And the same holds true for the like this reconstruction. So you can see that deltas, and you can actually do these 2 things. If you just take SIFT orientations, it's here. If you remove all the duplicates with the same key point positions but different orientations, this is second row. And then if you add the key points to again fill your feature budget, be it like 8K or 2K, and add like unique additional key points, it's benefit everyone. It's maybe not that huge for the camera pose, but it's much bigger in number of inliers. So you're like more robust. And the same works for the multi-view as well. Now, when you do matching, you can do exact matching, but it can be costly. If you match in 8K features versus 8K features, it's quite a lot of computation, because the cost is quadratic. What people often do is use some approximate search algorithm like FLAN in OpenCV, or some others like alloy and phase or whatever features. And it's important to remember 2 things. First, that you always need to check defaults, and as you can see that OpenCV defaults are quite fast, but they are not that precise. And so you need to tune your thing, and even if you tune your approximate nearest neighbors, it's not as good as exact nearest neighbors, although you can be quite close. And the same holds true for the camera pose accuracy, as it is just now percentage of correctly matched descriptors on each patches. And this is on camera pose accuracy, and you can see that with FLAN, for example, you drop a lot for SOSNet or HardNet, not that much for SIFT, apparently, or like even more for D2Net, although D2Net is not precise. Okay, you can also try to estimate shape of local features to normalize it. For example, if you're taking photo of the circle on the oblique angle at some wall, then it can be seen as an, and try to recover this ellipse. This was done for the Hessian-affine classical detector, or for the AFNet, which is learned this affine shape feature. So this improves your results for the number of inliers and also like precision of your geometry if you have like a huge viewpoint difference, so it helps. This is how it trained. I think I'll skip that. If you're interested, just check this paper. Repeatability is not enough, and then just check it. And does it make sense for the phototourism data? It turns out that not really, because okay, here is VL fit features like DOG. This is like SIFT, And this is OpenCV, this is FieldSheet implementation. And if you add this class affine estimation from Hessian affine, you can improve or be worse. Or if you add some learned estimation, again, you can be worse or you can be a bit better, but this is quite negligible difference. For the non-extreme viewpoint changes, it does not worth it. And this is, I think, for like just specific numbers, the test set, and you can see that, okay, with you can improve very little here, or for multi-view again, dog affine versus SIFT is even a bit worse. For Hessian it improves, but still worse than SIFT, so not that huge difference. Now detectors. And first, which is so the most of papers now, maybe it will change, but often about local feature descriptors, because it's important component and because it's easy to formulate as a task for CNN learning. But there is this work from 2015 on the static cameras. So it was taking these static web cameras and then trying to match in the different weather conditions of the day and so on. And what is interesting that sometimes we have matched them, sometimes we failed because of descriptor, and basically descriptor can improve your result 2 times, but to improve it like 8 times, we need to have like ideal key point detector, which is not that easy to do. And here are results, and actually we have compared the local feature detectors before. Maybe I was not kind of getting attention to this, but okay, here. First, the DOG, like SIFT, is better than the binaries things and or the learned things like DTONet, R2D, Superpoint, and also it is better, or at least on par, than the other classical local features like MSR, Hessian, Harris, and so on. So the SIFT detector is a way to go. Very good and very safe. Now, we can visualize the key point matches, and I think more interesting is this right part. The blue points are those which are used in final 3D model, which outputted, and the red ones which are not matched. That for example, sorry, that for things which are the problem of has much less spread. That's why we could have problems with the camera pose estimation. Surf is doing a very bad job at filtering something at the ground, or with detecting corners and again not spread well. And the SIFT is actually quite good detectors, you can see. And what is the funniest part? That is just as this. DOG is just cleverly computed template matching of this kind of blob, and that's it. So it's like incredible. So what about joint detectors and descriptors, which are mentioned by Vasilios? So here is again as a reference DOG, like SIFT one, and here are different things. And as you can see that KeyNet, which has lots of handcrafted components inside as well as learned, it can be seen as cleaner version of a DOG. So it's filter all this background stuff. It's also well spread. The R2D2 is, you can see that it's kind of very well spread, but then lacks of some precision, I would say, on the key points. The DTONet, as it's mostly, again, it just like a swarm of points, so it's probably get all these points like very repeatable but not very precise. And instead of one good point, you have cluster of points, and then it gives you some problem with matching afterwards. And for SIFT superpoint, it was trained to output corner location, and if you look at it and zoom in, you can just do it with slides download. You can see that it's very well captures the corners, and it's very reliable, but if image is not that rich on corners, you are in trouble. And here is a comparison to an example. Superpoint doing well, but it lacks layers. 51 is fine, but if there was some illumination difference, it would be worse. And if we reduce it 2 times, then it would be probably not enough. As in for D2net, 26 in layers is not that good enough for this model. As you can see, this blue one is pretty imprecise. So this is a thing, and if we combine all things together from the naive matching, like you take SIFT, you do, well, not very naive, but kind of like naive in a good way. So you pick lowest first to second nearest neighbor ratio, you use OpenCV RANSAC because why not? And you SIFT, you have very little number of inliers. Then if you just use this presentation and say, okay, I'll fix my orientation, I will use the hardnet, I will use a better matching strategy, I will use better RANSAC, then you can see that your results can improve almost for free, and be much, much better. Now, if you really need to match something, you can go for the thing which was originally proposed in a SIFT paper, but it can be done in a more fast and clear way. And what is actually the idea is very known to the deep learning practitioner by the name of test time augmentation, which means that instead of having single prediction, we synthetically augment your image and then average predictions. Of course, you cannot average just key point location, so you pick everything, all the key points, and use instead of 8K features 10,000, 50,000 features, which is quite a lot, but sometimes you just need to match a couple of images, whether it's an image registration problem or whatever. And this works like this. So we have images, we synthesize artificial views from this you can synthesize, emulate different views. So then you use some detector and descriptor of your choice. For now, I would use hardnet with SIFT or probably Hessian affine or Hessian offnet. You match RANSAC. If you have low inlier numbers, you can try to have more. And that's how you can match some things which are very, very hard to match. Like the things you cannot match with the deep learning methods. So without view synthesis with classical, you cannot match this as well. But if you add this view synthesis, you can actually match as hard images as this. And this concludes my presentation. So I would like to give you some recommendation and answer questions. If you have them, I'll now will check the YouTube chat. So to conclude, if you don't need correspondences, just don't use local features. For example, if you're doing image retrieval, where you actually have image of some landmark or whatever else, and you need to output other image, you can be well off with global descriptor. They are very, very good, and like a gem descriptor. If you need to use local features, just try OpenCV root SIFT. It does not have root SIFT, but root SIFT is just operation taking square root of your descriptors and L1 normalize them. So it's 2 lines in any code. Use proper RANSAC like DegenSAC or GC RANSAC. Use proper matching. And basically, that's it.
Thanks. So do you have any estimate about why affine net doesn't improve a lot the results in the matching benchmark? Does it mean that the image pairs are not that extreme viewpoint?
I guess yes. And this is one more thing is actually, if you, and this will be presented by my student on the Friday workshop. If he try to learn the best hardnet or sourcenet for the matching, and it turns out therefore there's this exactly data set having too many augmentations actually hurts. And my intuition is that, imagine if you have two key points very close, and if you're too robust, you probably can match wrong one. And because of the high feature budget, like 8K features is a lot. So you can be like a very early spawned. It can be very different with 2K features is actually what I'm going to try AFNet with 2K features. I think it should improve, but I haven't tried this yet.
There were a couple of questions in the YouTube chat. So one was, if you have benchmark results for objects that are not near buildings. I tried to answer it a bit, but you can also give your own.
Okay, so that's hard. So couple of sequences in our things are not buildings. One is this like, I don't remember proper name, but this for America in this what is this, a huge in Yosemite statue, and another is this Lincoln statue, which is also like very non-planar, I'd say, very untextured, but mostly yes, it's about the buildings. And the fair answer is just because this kind of data is easy to get, right? And that's the problem.
Okay, thanks. Yeah, I think you can answer more questions in the YouTube chat if they come up.
Okay, can I? Okay, sorry. I'm trying now.
There was another one about dense versus patch-based methods. So if you have any
okay, so far patch-based methods are better. As actually, if you compare, if you check these results, I'm now scrolling. So these end-to-end things like R2D2, SuperPoint, they are dense. They are densely extracted, and then they're filtered to be sparse, but they're still dense. So it is good that you have more context, but it's worse in two terms. First, in terms of geometrically precision and picking the correct scale. So if you have large scale change or orientation, you're in trouble with these methods, at least as you're now. But patch things can be slower, but actually if you use something like Kornia to extract the patches on GPU, it can be very fast. It can be, and it takes much less memory. Imagine if you have like very high resolution image in dense, you will never fit this in the memory. Or you can, but with batch size 1. For sparse method, you can easily fit much more. So that's the advantage. But yeah, they are like integrating less context.
Okay, so there's another one regarding ground truth from ColdMap. I think you showed median error, but wouldn't a histogram of correct poses at different thresholds indicate more if the ground truth is trustworthy?
Well, this is what we showed. We have this histogram, but basically we have, I think, maximum error, which is for some outliers is like 4 degrees or maybe 2, which is much bigger than this is maximum error. And and you can see this by mean error, because mean is not robust. It's out mean, and this is still very close to the median.
Okay, thanks. I think that's it from the questions from the chat. So I think maybe Edgar can now start.
Trying to switch this hosting thing.
Oh, actually, there is one more.
Okay.
For reflective surfaces, is there any advice on what methods to use when
for which services?
Reflections, when there's like mirrors or windows.
Okay, so what I would use is to use pre-processing. Like there are a couple of papers I think on this CVPR on like reflection removal, and I would use this as a pre-processing method and then do local feature matching, because it's very hard to do something with it when you're only local, right? Okay, I still can't. So
We can wait probably a few more seconds to see if there's any question, and then we can move on. So until we wait, yeah, just wanted to say that Edgar's talk will be a bit about how to do end-to-end networks with Kornia, which is an open source library he started, I think, right? And then, or together with Dimitro, later on they joined forces to improve it and to make it what it is today. And I think they have lots of stuff to show with respect to how to do end-to-end pipelines there. So that would be very interesting to hear.
Yeah, so yeah, should I start, or do you want to wait a couple of minutes?
I think there are no more questions, so we can always, so Dimitro can always answer them from the chat, so we can move on, I guess.
Okay. Dimitro, could you stop sharing your screen?
you're a host now. I think you can do. Okay, stop. Okay. Done.
Okay. Yeah, cool. Yeah. Okay. Okay. Can you see well my screen?
Yes.
Okay. Cool. Okay. Yeah. So yeah, let me introduce myself first. As mentioned, Vasilis, at the very beginning of this presentation, I'm Edgar. So I'm a PhD student at the Computer Vision Center in Barcelona. I'm also working as a research scientist at the Robotics Institute, also in Barcelona. And I'm also part of the OpenCV steering technical committee, helping, leading the Kornia project there. And along with Dimitro, that at some point he joined this effort to maintain this library. And this talk will be about it will be two parts. So first part will be a quick introduction about Kornia, what it is, the different components you have. And the latest part will be hands-on on Kornia. I will go through a couple of examples showing different capabilities that has the library. And in this case, for the topic of this talk, local feature matching. And in the end, Dimitro will show a small example about the end-to-end feature matching using a complete Kornia components. Okay, so yeah, let's get started. So way back when all these deep learning frameworks start to appear, like TensorFlow, PyTorch, all the whole computer vision became like the classical computer vision became like kind of obsolete, and the people that were doing this classical computer vision, we came with this question: where is the classical computer vision in this deep learning area? So, and the question was more or less this one: that there is this black hole area in classical computer vision for deep learning. And this is the reason why with Ethan and Gary and some folks related to the OpenCV Foundation, we started this ambitious project. It's called Kornia right now. which is an open source differentiable computer vision library for PyTorch, which basically it's a reimplementation of many of the functionalities and components from OpenCV, all re-implemented in PyTorch. So it means that it's all written from scratch using plain PyTorch operators, which takes several properties of PyTorch. Right now, the project, it's as the name says, it's an open source library. It's open source and it's in GitHub. It has an Apache 2 license, and right now it has up to 2,400 stars in GitHub, more than 200 forks. We have more than 50 contributors, and it's been used by right now several projects. So, and let's talk about the core features of this library. So basically, as I said, Kornia, well, the design principles that we tried to take while designing the library was to keep the main properties from PyTorch, at the same time to have the simplicity of the curated list of computer vision algorithms that OpenCV has. And basically, we wanted to, well, I think Dimitro mentioned at some point that in his talk that Kornia, we like to say that it's the OpenCV in PyTorch, right? At the same time, as I was saying, it inherits the different properties from PyTorch, like the differentiability. We have a transparent API, meaning that we can run the different operators through different devices like CPUs, GPUs. Right now, we are also starting to try XLA devices. It enables parallel programming by default. You can also run the different operators in a distributed manner using the native distribute API in PyTorch. And also, it is able to be used for production just using the just-in-time compilator from PyTorch. So basically, here there is this snippet that more or less show with very few lines of code, you can do all this. You can have all these properties I just mentioned. You can load an image in a batch with just a single call. You can send to a CUDA device. You can very easily define a sequence of operations and define your computer vision pipeline. Making use of the distribute API, you can send this pipeline to a set of different devices. And finally, once you have all this, it's very simple to infer over this pipeline. So this is more or less the traditional things that you could do using, for example, OpenCV. But right now, you can very easily integrate more or less the same philosophy as OpenCV, which is there's the simplicity of the API using PyTorch. So now I'm going to present the different functionalities we have in Kornia. As every computer vision library, it's split in more or less the different big areas in computer vision. So, for example, we have a module for data augmentation, which basically we make use of the Torch distribution package to sample different random distributions to apply on the images. And this package is compatible with Torch Vision. And it allows you to run the augmentations in batch using GPU. Now we are starting, as I said, trying XLA devices too. And also we added this cool feature that you could return the spatial transformations you apply. And also, in case you have different transformations, even you could very easily chain it. I will show one of the examples I will show. It's related to this, so I will give more information once we get to the examples. Then we have this module for image enhancement, which basically implements different operations for image normalization. We have different algorithms like ZCA whitening. we can compute their image histograms in 2D, well, 1D and 2D. We are also planning also for histogram normalization. We have if you are familiar with PyTorch, probably you know all these adjustment, contrast, brightness, gamma, hue, saturations. We have all these implemented. They are fully differentiable. So as I said at the very beginning, everything it's re-implemented from scratch using PyTorch. So it means that you can use all these operators to differentiate over your functions. Then we have this module for color space conversions. We cover different algorithms to convert from one space color to another. Then probably this is the most important for this tutorial, which is the 2D feature detection module. In here we have several algorithms, for example, for classical feature map corner detection, like Harris, Hessian, the difference of Gaussian that we have been covering during the talk. We have even this high-level API for the scale space framework, which is very modular. You can plug the different detectors, different models for non-maximal suppressions, for orientation, shape estimation. We also have, apart from that, these small models that I was mentioning, like for computing non-maximal suppression, to compute the convolutional softmax 2D operators, even in 3D, in case you want to do it in the scale space volume. Then you have this local affine frames API, which is basically a set of functionalities to work on the detections coordinate, so that you could build different loss functions over the geometry of the key points. And finally, we have this differentiable SIFT implementation that Dimitri implemented, I think, in Affinet at some point, that later was introduced to Kornia. And recently we introduced a couple of deep descriptors. Basically, we introduced a hardnet and sourcenet, so that people, for example, people working or trying to benchmark for the image matching challenge could make use of these state-of-the-art detectors. Then we have also this image filtering module, where we have like generic operators for applying 2D and 3D filtering. Along with these high-level functionalities, we have these small kernels API, so that you could parameterize different kernels, like creating Gaussian, Laplacian, or Sobel kernels to be applied. And then we implemented more or less high-level algorithms for computing median blurrings, box blurring, Gaussians, or motion blurring. Similar to this, we have the edge detection module, where we have different classical edge detection algorithms like Laplacian, Sobel. And also we have this interesting spatial gradient operator, which basically it computes the raw derivative in 2D, and also we have the 3D version of it, which is, I think, very interesting to explore new ways for research. So that it not only works with images, but for example, imagine you could feed a feature map from a network and then compute some derivative to it. So I think these kind of operators are very interesting to start playing with it. Then the geometric module. This is probably the biggest module we have. Actually, it was the first module in the library. Just as recall, the Kornia first was a very small package for doing geometric transformations, that then evolved to what what you see right now, to a more generic computer vision thing. And it basically has several high-level routines for doing rotation translations, in general, affine transformations. Then we implemented also to perform Gaussian pyramids, different cropping functions, flipping functions that can be used for data augmentation or just, as I said, everything in Kornia works for tensors, image, well, feature tensors. Your input doesn't have to be RGB images. It can be just multidimensional tensors. And also in this geometric transformation model, we have then more low-level operators. Basically, this is kind of actually this where exactly start the first packets, where we were mimicking some of the functionalities in OpenCV. If you have been working in OpenCV, you will recognize these functions: warp affine, warp perspective, that basically will take the 2D affine transformations or homographies, and you could warp images or tensors. And then we have these also functionalities to recover, given sets of points, the perspective transformation. And then this rotation, rotation matrix that will compute for you the transformation to perform the rotations. So this is more or less the initial idea for the geometry packets, and right now we are trying to expand more on 3D geometry. So we have this pinhole and perspective camera API, so that you could project and unproject points to wall, from the wall to the image plane, and vice versa. Then we have this small API for conversions, where you could convert points from the homogeneous to Euclidean reference frames. Also, different conversions for rotations, like going to the rotation matrix, quaternion and axis angles, for normalizing pixel coordinates. Then several operators to compute subpixel accuracy based on convolutional operators. And finally, that this is something that we are working right now. We recently include all these functionalities for epipolar geometry, like algebra and structure for motion utilities, that basically are operators for computing, or for manipulating projection matrices, fundamental matrices, essential matrices, everything related to structure for motion. And finally, I would like to talk about this. We have these small packets, which is basically a small compilation for different specific loss functions for computer vision, like for image reconstruction, like the SSIM or PSNR operators. Loss functions like focal loss for semantic segmentation, and then specific ones for comparing heat maps. So this was basically the main functionalities we covered in Kornia. So now I would like to very quickly, before going to the examples, to talk how to start using Kornia. Kornia, it's very easy to install. You can get it from pip. Just by pip install Kornia, you will get the latest version from Kornia. You could also install it from source, in case you can wait until the next release. And one thing that I would like to notice here is that Kornia, it's totally dependency free. It only relies on PyTorch. So you don't have to install, compile anything. I'm not quite sure, but probably in case you don't have even Torch installed, once you install Kornia through pip, it will get the required version. So it's very handy in plug and play to start using it. And then, as I was saying, we rely on Torch tensors. So one of the principal designs for Kornia was that we wanted all the operators to consume torch tensors. So every single input for every function in Kornia will be a torch tensor. And here, well, this is a small examples just to showcase this. But this is something that I would like to remark, that every single input in Kornia assumed to be a torch tensor. Then finally, as I've been saying during the talk, we are compatible, or we try to be compatible to OpenCV. Every single function tries to be very similar in the way you will use it in OpenCV. Here you can see that it's very, very similar. The gap between using Kornia and OpenCV, it's very close. So in this case, using this Gaussian blur operator, you can just open, well, read an image in OpenCV, and then, well, in the case of Kornia, you have to convert it to a torch tensor. We have this utility function to convert one NumPy image in the format from OpenCV to torch, and then you will feed this image to the Kornia operator, and you can see that the API is very similar to OpenCV. Another example, this warp perspective function used to warp images. You can see that the behavior will be very similar. Then I wanted to mention that the ecosystem integration, and the ecosystem, I mean that Kornia, it's also compatible, for example, with a torch vision in this case. So for example, the API for data augmentation I was mentioning, it's very, we try to make it very close to torch vision, so that people that was using torch vision could very easily use Kornia to make use of the specific use cases we have, for example, for returning the transformation and such things. And also for ecosystem, I mean, to integrate Kornia in other training systems like PyTorch Lightning, we have, I will point later to it, we have a couple of examples how you can easily integrate Kornia in this PyTorch Lightning training system. The same for, we recently introduced Kornia into Kaggle. So now Kornia, it's part of the Kaggle kernels. You don't have to do anything. It's there for free. You can start using Kornia in Kaggle. And also we have in one or a couple of examples that in Metro implement using Kornia in FastAI. So in the end, Kornia, it's a high-level API that it's very flexible and can be used in, I would say, every single PyTorch-based training system. So as a future plans, we are working, well, as I said, we were working right now in a structure for motion, but we are also interested in 3D transformations. I think something that's going to happen in the next weeks. We'll push, for example, an extension of this warp fine and warp perspective for the case of 3D volumes. We have well, I have implemented this warp projective operators that you will be able to rotate the features, a volume of 4D features using a 3D transformation. And by using that, probably we will implement more high-level operators around it so that we can perform 3D transformations. And also another interesting thing that I think right now it's kind of this task. It's for converting all the operators so that can be torch scriptable, so that we can make use of the just-in-time compilator from PyTorch to make to get better performance in time. So yeah, and as I said at the very beginning, we are open source. Right now we have, I would say, we're starting to have a strong community. So we receive every week at least a couple of pull requests. People is interesting. So everyone is welcome to contribute to the library and join the community. And then some information for users. We use the PyTorch discussion forum for question and answers. So if you have any question, just go to the PyTorch discuss. We have there a specific tag for Kornia under the vision tag. So yeah, feel free to ask questions there. Myself, I try to go there time to time to answer some of them, but I'm pretty sure, you know, the PyTorch community, it's very large, so I'm pretty sure that someone could also help answering questions. Then something that I will go through very quickly right now, it's the official documentation. So we try to keep the code documented. The documentation, it's auto-generated using Sphinx, and we host it in read-the-doc. So every function, just check the documentation. I think Dimitro tweeted before that he's using that because I think it's very helpful to have documented code, and we try to be very precise documenting the code and with all the input, with the input shapes, the outputs, so that once you read the documentation, you can start very easily to use this functionality. So I will go through that and we'll quickly show the documentation. And then for people more interested in developing, we have all the time open issues with the actual roadmap we follow for each version. So we have there a list of items with the different tasks we would like to achieve for the next version. So just feel free to check it out and volunteer yourself. So it happened in the past that we just put some feature requests from the issues we got, and then just people started to volunteer. So again, feel free to visit the roadmap and check it out. And finally, if you are really into it, developing, we have also these contributions welcome documentation where we describe step by step the different things you have to do in order to start developing in Kornia. Extra material. This will be the second part of the talk that I will go right now. It's we have a repository called Kornia Examples, where we have a list of with different notebooks and collabs with different cases using the different modules for Kornia that I will show very quickly a couple of examples right now. And then within the documentation, we have some small tutorials, quick start tutorials, so people start to get an idea what's Kornia. And I think that's it, this first part of the talk. So if you have any other question, just go through the website, kornia.org. You have more information there. You have there the paper we got accepted in the work 2020 a couple of months ago, before all the COVID stuff. And then following Twitter, we try to be very active more and more, because we have been noticing that a lot of projects and people start using Kornia right now. So we try to keep there all this information updated with the news and new projects that are using Kornia. And of course, go to GitHub, check the code. You will have all the information there. Okay, so let me go now. As I said, I will go to the website. This is kornia.org. Let me quickly show you what you will get there. You will have here different links to the documentation, the tutorials, the forums, some news that I think it has to be updated, but you can get there more or less an idea what it is, the papers, different organizations that are supporting the project, like the Computer Vision Center, the OpenCV Foundation, several startups, PyTorch itself, AWS. It's also hosting the part of the testing framework. But yeah, the interesting thing that I wanted to show here is the documentation. If you go to the documentation, you will see here that you have all the API. Just to pick a random example, if you go to Kornia color and you go to color space conversions, you will see that you have the API here. We try, well, we try to keep the code with typing so that you know each of the inputs which type of variable it is. We have defined all the parameters, return values, etc. So yeah, just check that the documentation, and as always, if you have any issue or any recommendation, just feel free to issue a ticket and we will try to improve it. Also, another interesting thing that I was mentioning is that we have some embedded tutorials here. I will go to this Hello World tutorial that, for example, it shows how to read an image, for example, using OpenCV. Then how you can convert it to a torch tensor, apply the classical. Well, you know that in OpenCV you read the images in BGR. In this case, we convert using Kornia BGR to RTB, and then finally we use Matplotlib to show the result. But this, I will say, is the hello world for Kornia, just how to read an image, convert it to torch tensor, and apply a minimum vision color space conversion, and just to plot it. Okay. So yeah, I think I will continue with now a couple of more specific examples for the topic of this talk. As I said, if you go to GitHub under the Kornia organization, you will see that here we have several projects. The main one is the Kornia project, which is the library itself. We have several projects here for benchmarking, the examples that we will go right now. And yeah, here we have this PyTorch Lighting conference sheet, which it's a template for start using Kornia, in this case PyTorch Lighting. Just check it out. We have different things, but let's go to Kornia examples just to show you what you have here. And as I said, we have a list of different notebooks. I'm not sure if they are all Colab notebooks. Most of them, they should be. And the first one I wanted to show was this one for geometric generate patch. So basically, in this example, we show how we can use the different components from Kornia to generate local patches from images. Okay. Let me go to the Colab. Well, I already have it here. Okay. So basically, in this Colab, okay, here. Let me run it very quickly. We will install Matplotlib for visualization. I will download just initial image. Kornia, you see here that I directly pip install Kornia from source, and you will see that it's very fast. Okay, it's done. Now we have Kornia. We have here already some functionalities that I use for for plotting images and reading images using OpenCV. And here, yeah, there we go. Yeah, and in this first block, we use this, well, in read functionality, as I said, it opens this image in OpenCV, and then it converts to from RGB to RGB, and then we plot it. Okay, so this is very simple. And here, I would like to show this random crop operator, which basically will randomly crop patches from the size we specify here, in this case, 64 by 64. So, and as you can see here, we define this random crop instance. So this will be an instance of this operator, and then here I have defined this for loop. In this case, I will generate 15 different crops of size 64, and then we'll plot it. So here is running in CPU, but as Dimitro said, you could do it in GPU, which is very fast. Well, we are in Colab. We can increase this number. We can get more patches. Okay, we could even change the size of the patch. Well, but it's something that I let you start playing with it. And finally, in this next section, I would like to show this random affine operator, which is something that we use very often. We do at least data augmentation for features, local feature matching, which basically this operator will augment every patch with a specific transformation. Here I have defined it. This is the rotation minus plus 15 degrees, and here it's a small translation I want to apply. And here, this is the feature I was mentioning before that allows us to retrieve the transformation applied to the augmented patches. So basically here, in these 2 lines, we define the instances for these operators. And then in this line, so we create this batch of patches. And then finally, once we have this original batch of patches, then we apply this affine transformation. And as you will see here, we will retrieve the transform patch, and then also we will retrieve the batch of the affine transformations that were applied to this to these original patches. So basically, what I want to show here in this example is that as you see in the image on the bottom, you will see that on the left side we have the original patch that we cropped from the image, and then in the middle column we have the transform patch. But that in the last column, as you can see in these 2 lines, well, 3 lines of code, we have inverted the transformation. So we are using here this world perspective where we input the transform patch and the inverse transformation that was originally applied, so that we get the original patch. So here on the right side of the image, you will see that we will get the original patch. So there is this black borders effects that were produced after the first transformation. But you will see that the right image is completely aligned to the original patch. So this is something that it's very useful for research. In this case, that you want to do some synthetic data augmentation, because yeah, there are now a lot of papers using of this kind of consistency loss that it's very handy to have, well, to generate the synthetic data and then to retrieve to go go on back to the original transformations. So this was the first example. I'm gonna go now to another example that it's more related to heat maps. Okay, let's go here again. We'll start Kornia, Matplotlib. And here, in this case, I would like to show this operator that it's called render Gaussian 2D. Okay, so that basically what it will do, it's given a tensor of 2D coordinates, we will be able to render these 2D coordinates in a heat map. So basically here, what I do is I generate this random tensor with a size of, well, in this case, batch 1, but n will be the number of key points I would like to generate, which is 250 key points. The last dimension is the axis for the coordinates. We'll have x and y coordinates. And here I generate this uniform distribution that I will weight by the width of the expected heat map size I want to do. And finally, you see here, well, I forgot here to mention that I will define here the standard deviation for each of the blobs, well, the key points blobs I will generate. And here, as you see, the operator is very simple. You feed it with the XY coordinates, the standard deviation, the expected output size, and finally here you will get this a stack of heat maps that will have the following shape: the byte size that we define it at the beginning, and then we'll have one heat map per each key point. So, and here, let me show how I plot this. In this case, I picked the first generated heat map. You see that we have this small Gaussian render of it. Then this other one, and the final one, I just accumulated all the generated Gaussians in this single heat map. So probably those that are working on detectors are very familiar with this kind of heat map that usually is a result of the detection functions. And another functionality that I wanted to show, once we have, which is another typical step that we use after, well, for extracting the coordinates from Heatmap, it's the non-maximal suppression. So we have also implemented this non-maximal suppression. And here, as you can see, I take this initial generated heat map, which I accumulate over the different axes. So now we will have this batch 1 high width tensor, and then I feed this tensor to this non-maximal 2D suppression operator. Here, this tuple here indicates the window size, so this will apply a non-maximal suppression within a 3x3 window. And well, and you can see here the result. On the left side, you have the original heat map, and on the right side, you will get the filtered heat map based on this constraint applied from the non-maximal suppression. And this is another tool that I think it's very useful for people right now, including myself, working on detectors, that could be very easily used to add it as for example, a loss function, to include this kind of constraints as a loss function. Because as I said, all the operators, including that one, it's implemented in a way that it's differentiable. So any of the inputs could be a torch variable that contains gradient. So why not differentiate over that? Okay, so I think that's it from my side. I'm not sure about timing, but I give the last minutes to Dimitro that will go to a full example for image, well, local features matching, if I'm right. So yeah, let's go ahead, Dimitro. I guess I have to stop sharing my screen.
Yes.
Okay, cool.
Can you allow screen sharing, please? Click on me and allow, because now it's blocked.
Make host.
Or you can make Dimitri host.
Yes.
Okay, cool.
So can you make me host? So click on me and then there was this. Okay. Great. So where is sharing screen? Okay, I will show two examples. One is they show that again. So this is really work in progress. Well, is it not sharing? Looks like it's not sharing. Okay.
You can see the collab document.
Yes, great collab. So installing, as you see, that I'm installing not from the master branch, unfortunately, because now we have active development and different features are not yet well tested, documented, and merged. That's why I'm doing. But this is like latest what we have, and this machine implements everything. We don't have RANSAC because RANSAC is not differentiable itself, but we have robust estimators like iterated related least squares, which is used in deep method. They are not as robust, but they're differentiable, and so I'll show you this example of how I will match the images with everything. Okay, so it's downloaded. So first I do import. So one is very useful function is visualize your local affine frames. And this local affine frame, this is actually all features. So key point, scale, orientation, and shape possibly. And this is image pair from the H patches. H patches sequences like full images on patches, and we are going to match it. So what I do, I define a detector, which is a highly modular scale space detector. First, I have how many features do I want to detect. Then the response module, which is Hessian, or it can be Harris corners or good features to track Shitamashi corners. Also, the non-maximal suppression model, which can be done with a quadratic interpolation as done as in SIFT, but unlike SIFT, there are some differences to make it differentiable. And it makes things worse, but kind of if you need to work, so if you want to backprop, you need to use soft operators, not hard. Scale pyramid model, so which means that this is number of levels of pyramid, so how precise I would like to detect scales. This is sigma, this is my patch size, this is number of image. Do I want to do some feature orientation, or I can just comment out it and there would be no feature orientation? Local affine shape estimators. It is the same as in Hessian affine. Again, all differentiable. This is orientation as in SIFT. Measurement size, which means that when I detect key point, this is like small block, and you need to enlarge it by 6 size. So 2 times different from OpenCV, so it's equivalent for OpenCV 12. So, and for the descriptor, we use pre-trained hardnet, or we can use actually SOSNet. Can we? Yes, we can. So let's use the best detector descriptor. And then, so because I don't want to backprop here, so I detect local features and responses. I extract patches from pyramid. This is a very important part because, okay, magic number, so it doesn't work somehow. Okay, go back to hardnet, it's interesting. Maybe it's some cached problem. Okay, it's downloading. Okay, so when people extract patches, they often do it without pre-smoothing, and it results in aliasing, and this is very bad for descriptors. So one need to extract patches from pyramid, then they would be nicely smooth before extraction. Then we match, and this is matching strategy which I mentioned before. This second nearest neighbor ratio with mutual check. And then we find homography with iterated related, and here are results. Here are affine features, and you can see that they are actually affine, so they are ellipses, not circles, and this is what has been matched. Or what we can do, we can change detector. Now we could use corner detectors, like with features to track. What else? We can also use SIFT, and probably we would like to use root SIFT. Where is root SIFT? True. So it's easy. So wait, it's running on CPU, and so that's why it's not extra fast. Yeah, so we found again also homography. As you can see, the features found are different. So that's it, and you can plug it into your some differentiable pipeline. Yet we haven't yet been able to match the results of classical library like VLFit or OpenCVE. I think we have 10 MAP points worth on validation. So for the upright hardnet with SIFT, you could have, I think, 0.77, and we are 67 so far on this image matching workshop. And it's often because of some nuances in implementation of scale pyramid. We find a bug recently there. And then another problem comes from that soft operators. But yet it's not bad, especially if you not to backprop through it. And now I will show this to a local feature adversary. Okay, no. First I change runtime to GPU, and so what I'm going to show here, that you can actually backpropagate through Kornia operators to image space and make the non-matchable images kind of force them to match. So what I'm so everything is downloaded. I open images, I put them in the tensors of the same site so I can use batch processing. So here is Kyiv Polytechnic Institute in Kyiv, Ukraine, and here is a graffiti in Oxford. So they obviously don't match at all. And let's so we have SIFT detector, we have some descriptor blob Hessian. So here we go. So we detect some features. We visualize these features. Okay, is it CUDA? Yes, it's CUDA. Fine, so we visualize. So these are detected features. Then we try to match them and see that there are some kind of random matches, mostly are like background or edge features, and you can see that geometrically they would not survive any RANSAC check. Now, what I'm going to do, I'm going to run optimizer on the input. So I would like to change input image to be that it would be matchable by this Hessian detector and the SIFT descriptor. So what I do, they work in grayscale, so I use this differentiable conversion to grayscale. Now I clamp everything to be in the valid image space. Then I run the detectors. I extract patches, descriptor. I match features. Now, this is not like some magically differentiable image-to-image thing, in the terms that if, because features are local, they cannot backpropagate through whole image. We need to find the features that have similar location so that they can be backpropped through. So we have scale loss, detector loss on scale and X and Y, and descriptor loss. So which means that we want to detect the same key points in the same location, and they should be close in the descriptor space. Which is, this is first to say, this is how we basically train HardNet. And this is, we use this to alter our image, and then we would like to be new image similar to original image. So it's kind of adversarial example. So we're not going to fool humans. In that sense, that is would not be imperceptible. But this is just to example to demonstrate how it is differentiable and what you can do this. And so you can see that XY reprojection loss from one image to another is so far the same, but number of like descriptor loss goes down, number of matches goes up, number of the detection in the same locations first goes down, then go up again. We have more descriptor matches now. And then I will have this 3 more log strings, and then I'll show you the result. So this optimization goes in real time. I mean, not in real time in terms of speed, but right now. So let's plot it and match it. So this is altered a version of graffiti. So you can see these patterns which appeared, which are required to full Hessian detector and SIFT descriptor simultaneously. So let's check if they survive RANSAC. Yes. So as you can see that these key points are in the very same location. So it's homography is identity matrix. So we have these things, and so this is just very zoomed in features. So you can see these weird patterns which are needed to alter our descriptors. And here, so you cannot say that it's like adversarial, that you cannot support it. Of course you can, but this is very naive function. One could optimize, one could try to use the things to improve some operators for detectors, descriptors, or so on. So that's what I would like to show. And I think that's it. So if you would like to collaborate or use Kornia, and by the way, we are happy to promote all projects which are using Kornia in Twitter. So if you're using Kornia for local features or for augmentation or whatever, just cite it or drop us a message and we'll share about you. And I think I'm done here. Stop sharing. Any questions? Could you please post link to the notebook? Okay, sure, I'll do it right now. So this is in Kornia examples. I just put this, I like re-put this into Google Colab to save some time, but basically that's it. Any plans to support other deep? It's hard to TensorFlow and MXNet. I mean, Keras started to support a lot of them, but now Keras is for the TensorFlow, right? So it would be cool, but we don't have so much resources. Maybe Edgar would surprise me now.
No, not really, because actually everything it's creating from scratch using PyTorch, it will mean like rewriting the whole thing probably in C++ on something very low level and then export to the different frameworks, which could be very cool. But as you said, we have not much resources yet, and I don't think it's feasible at all. But there is another way to do somehow that. It's through exporting the operators to ONNX, which is another interesting path to explore. So in theory, the way it's everything implemented in PyTorch, you could export any definite operator into ONNX. And I'm pretty sure, not sure about TensorFlow, but MXNet, I think it's very ONNX friendly. So I think it's something that would be nice to explore at some point, to trying to export some of the Kornia operators using ONNX and trying to load it, well, import it in that case in MXNet. I'm aware also that OpenCV it's pushing for that as well, to try to be compatible with more and more ONNX model or formats. So to me, that would be the easiest way.
Okay, I think if there are no more questions, then we're a bit.
So I wanted to mention something that about from your talk, Dimitro, that well, you were claiming that OpenCV you don't have to use OpenCV for RANSAC. So I agree with that. But I just wanted to comment that there is an ongoing Google Summer of Code project this summer that it's trying to refactor the whole RANSAC framework. Yeah, and it's planned to implement there many of the algorithms that you were showing in your presentation. I'm not quite sure when it's gonna be updated, but probably for sure for the next release. So
it's actually interesting if you think how many papers maybe could have different results if they were not using the OpenCV RANSAC, right?
Yeah, that's true. Yeah.
It's funny that so sometimes people say, okay, OpenCV probably it's not fancy. I'll use USAC as a kind of, it was sold as a RANSAC, which have like super universal, but implementation is bad and it's actually even worse than OpenCV RANSAC USAC. This is incredible.
Well, we'll see after this new refactoring for the RANSAC framework. Well, probably you know more details about that than me, because it's from one of the guys of your lab.
And if Eric Brackman would have some free time to implement some ng RANSAC into Kornia, we would be happy. So it's still maybe we will have RANSAC in Kornia as well. It's just hard to do it, to make it differentiable, but there are ways how to do it, so maybe we can.
Well, actually, it's the conversation we had at some point, no? How to start to define. Now we have the detectors, the descriptors, how we should shape the API for matching and other exotic things, like to make it easy in the way we designed it, the scale space framework, that it's very modular. How we can continue, the whole pipeline, how to define the API so that you can plug any components coming from networks. This is something that, well, it's an open question yet, how we should proceed with that.
So if someone wants to participate in this project, we would be happy.
Yeah. As I mentioned, one of the next goals is to grow on the structure from motion. We recently introduced this epipolar geometry, which is basically a porting from the OpenCV structure from motion that I implemented many years ago. So now I ported to PyTorch. So now we have more or less the basic components again. It will be nice, as you said, if anyone is interested to contribute on that people from SLAM, the guy from, well, actually from Kaolin and Grad SLAM, it's also willing to contribute on that. He already have some advanced work for Lie algebra that it's going to contribute to Kornia. And yeah, it would be great to kind of build some sort of a high-level API around structure for motion or even SLAM.
Okay, yeah, I think there are no more questions, so I think we can wrap up.
Okay.
So I don't know if Edgar, we can probably upload your slides to the website too, right?
Yeah, sure.
Actually, there is one question now. So is it possible to have a fully end-to-end SFM pipeline using Kornia?
Well, actually, it's what we were discussing right now. Yeah, you have, I would say, almost all the components there. You actually, it's funny that because a couple of weeks or maybe more, there was released this package for SLAM using pure OpenCV. How was it called? PySLAM, something like that. So, and I was kind of checking the main functions that we were using, and actually, all those functions we already have it in Kornia. So, and as I was mentioning right now, it's just a matter of starting a project, starting a new project using these functions and start building a new structure for motion or SLAM system on top of it. Yeah. So in theory, the answer is you could do it, but yeah, it's again a lot of work. And
so you could do it, but it's not done yet.
Yeah, right. But we're working on it. Yeah, let's say.
Okay, I think now this time there are no more questions. I mean, if there are more questions, I don't know how long the YouTube stream will stay up, so maybe we can answer by text, but I'm not sure if it will remain. So we'll try to put the recording in the tutorial website anyway. Yeah. And then everyone, I guess, is happy to answer more questions via email or anything else. I know you're both active in Twitter, so maybe you prefer Twitter.
Yeah, Twitter, or if it's something related to Kornia, just open issues in GitHub or even in the PyTorch discussion forum. Well, maybe I forgot to mention that we have also a Slack group. We have some sort of community more development based. But yeah, and if anyone want to get in it's open, so there's no problem to get anyone into it.
Okay, I think that's it for this tutorial. So thanks everyone for attending, and yeah, please check the website for the talk and the slides. Thanks.
Okay, bye-bye.
Thank you. Edgar, I think you're the host, so you need to stop the stream.
Okay.